In this video, we're going to talk about inertial reference frames and Newton's second law, which is covered in chapters 5.5 and 5.6 in the textbook. Okay, so first off, inertial reference frames. So, an inertial reference frame is a reference frame where Newton's laws are valid. So, which may seem like a strange thing to think about, but sort of a good example of this. So imagine you're in a car zipping along at 55 miles an hour, and you have your coffee and you sit your coffee on the dashboard for some strange reason, right? So if you think about, so if your reference frame is the inside of the car, right? So the inside of the car, in that reference frame, your cup of coffee is at rest. Now, let's say somebody pulls out in front of you and you have to slam on the brakes. Well, if you slam on the brakes, then of course your coffee is probably going to go splattering all over the place. So if your reference frame is the inside of the car, so the coffee was at rest in that reference frame, and according to Newton's first law, an object at rest should stay at rest unless some force comes along and acts on it. But if you think about it, was there a force that came and pushed the coffee cup over? And there wasn't actually a force that came and pushed the coffee cup over. And the reason why your coffee cup went flying everywhere is because as soon as you slammed on the brakes, the inside of the car was no longer an inertial reference frame. So since it's not an inertial reference frame, since you are accelerating at that point, Newton's laws are no longer valid and you actually don't expect that they're going to work. So, in general, non-accelerating reference frames are inertial. Accelerating reference frames are what we call non-inertial. And you have to watch out for these accelerating non-inertial reference frames because Newton's laws typically don't work. Now, another important fact, so if there are no external forces, it's actually always possible to find an inertial reference frame where the velocity is zero. And depending on the problem, oftentimes it's actually useful to find the inertial reference frame where the velocity can be zero. So another interesting thing to think about is, what about the Earth's surface? So is the Earth's surface an inertial reference frame? So actually, technically speaking, it's not, because if you think about it, if we just sit at one spot on the Earth's surface, well, the Earth is revolving, right? So when it's rotating, so we actually, if you think about the Earth's rotation, we actually sweep out a circle. So we go all the way around the circle in one day as the Earth rotates around. So we're moving in a circle, and since we're moving in a circle, we're actually accelerating. So the surface of the Earth is actually not an inertial reference frame. However, for most practical considerations, the amount of acceleration is actually pretty small, so it's usually safe to treat the surface of the Earth as an inertial reference frame. Okay, so which brings us to Newton's second law. So again, there's different ways you can phrase Newton's second law. Probably the most wordy is to say that the acceleration of an object is indirectly proportional to the mass of the object and directly proportional to the vector sum of the forces on the object. And of course, typically you actually phrase this as an equation. So the famous equation F equals ma. However, remember that the force is a vector, acceleration is a vector, and it's also important to remember that the force here is not just any old force. It is the net force on an object is equal to the mass of that object times the acceleration of that object. So, and oftentimes you actually see this net force written with a little summation sign, or you can, if you prefer to write this in terms of acceleration, so acceleration is the net force divided by the mass. And remember, I like the summation sign because it just reminds you that the force that you're talking about in Newton's second law, the net force, you have to add up all the forces on a specific object. So we'll see some examples of this in class. So, but just real simple example. So you could ask, so what's the average net force required to bring a 1,500 kilogram car to rest from a speed of 25 meters per second within a time of 5 seconds? So if we think about Newton's second law says the net force should be mass times acceleration. So we know the mass of our object. So what about the acceleration? Well, if we start off at rest, we end up at a speed of 25 meters per second. Our change in velocity, so we'll assume whatever direction this is, we'll call it the positive x direction. So our change in velocity is positive 25 meters per second, and that happened in 5 seconds. So the acceleration is delta v over delta t. So 25 meters per second divided by 5 seconds, which is 5 meters per second squared. And again, it's a vector, so the direction is this positive x direction that we define the motion to be in. So then the force is going to be the mass, 1,500 kilograms, times the acceleration, which we just found was 5 meters per second squared. So 1,500 kilograms times 5 meters per second squared gives us a force of 7,500 kilogram meter per second squared. So, since a kilogram meter per second squared, so that's the official SI unit for force, and physicists are lazy, so the tradition is we name our units after dead white guys. So this one's going to get named after Isaac Newton, not surprisingly, since this is Newtonian mechanics after all. So 1 Newton, abbreviated capital N, is defined as a kilogram times a meter divided by a second squared. Or another way to think about it, it's the force required to accelerate 1 kilogram at a rate of 1 meter per second squared. Now also the US customary unit is the pound, which I'm sure you've heard of. So the pound is actually a unit of force, and the pound is defined as the force required to accelerate a mass of 1 slug by 1 foot per second squared. So mass then is a measure of an object's inertia, so remember, and it's the property that determines how hard it is to change an object's motion.